Welcome everyone. So in the last class we have seen about our DC to DC converter, where we have discussed about our non-isolated solutions. Then we have started with our isolated DC-DC converters. Okay. So when I say isolated DC-DC converter, we will have an high frequency transformer which will be used in this type of converters. So why and transformer is used in this circuit? So the transformer will be providing as isolation between the primary and the secondary side of the circuit. So they will not be electrically connected, or we cannot travel from source to the load side through the electrical path. So there will be a discontinuity in the path, because we will have an transformer core which will be carrying the power in terms of magnetic field lines. So whenever we use transformer in our DC circuit, we should keep in mind that we should never allow it to get saturated, or else we can lose the converter circuit, because once the transformer saturates, it starts behaving like a transformer, it starts behaving like a good connecting wire. We have seen the limitation of our non-isolated DC-DC converters. So their gain was limited to 4 to 5 times, irrespective of the care taken in designing them. So because of the losses in the parasitic components, we will never be able to achieve gain higher than 4 to 5 times. The second limitation was there was no isolation between the source and the load. To address these challenges, we have started our discussion on our isolated DC-DC converter, where we will be using a transformer at high frequency, so that its size will be very less compared to the transformer which is designed for your power frequency. Then here it will be having compact size and design, because the transformer size will be very less. It can be used with high power density, so they will be having very less volume. So the converter size and weight will be less, and the efficiency also can be improved. There will be greater design flexibility with us. So now we will be no longer restricted to 4 to 5 times of our gain as per our requirement. We can just adjust the transformer turns ratio to achieve the required gain with us. Then transformer equivalent circuits. Okay, so we have in our simplified analysis, we generally consider the ideal transformer, where the current will be flowing through our primary side and it will be leaving on the secondary side. Okay, so we have also seen our dot convention. So as per the dot convention, if one of the dot is positive, at that point of time the other dot will also be positive. If the current is entering the dot on one side, it should leave the dot on the other side, because the transformer is a constant power device. So whichever is your input power, that will be given at the output stage, neglecting the losses in the system. Okay. So when I want to design an actual transformer, instead of idealizing or neglecting the losses, if I see what will be the loss inside the transformer, so we will get this type of equivalent circuit. Okay. So here we have an resistive component which is generally written as R1. On the secondary side we have R2, L1, L2 and Rm and Lm. Okay. So this R1, L1 is nothing but the primary side loss component. So what will be then? R1 represents active power loss. Okay, so it is because of the resistance of the wire which will be used to manufacture this coil, whereas L1 will be the leakage inductance. What is leakage inductance? So now we will have some leakage flux in the transformer. What is a leakage flux? Generally the power transfer takes place from the primary side to the secondary side of this transformer by mutual fluxes, or the flux lines which will be leaking both primary and secondary sides. But when we go for real transformer, we will see that some of the lines will not link with the secondary side. They will complete the path among themselves. The primary side flux will not link with the secondary side, and secondary side will not link with the primary side. So a small inductor which will produce this leakage fluxes is called as your leakage inductance. So that is given by L1. Similarly, on the secondary side, whichever flux are leakage flux, we will have a small inductor which will produce the equal number of flux lines which are equal to your leakage flux, or which are not participating in the power transfer from the secondary side. R2 represents the resistance of the coil in the secondary side, and this Rm and Lm are your core loss components. Okay, so in the transformer we will have an magnetic material, ferromagnetic core, which task is to allow the magnetic field lines to be created in the core, such that the power transfer takes place. So we do not have any ideal core material. Always there will be some loss associated with the core material. So what are these losses? There will be two components again. One will be Rm, which will be representing the core losses, and Lm is the magnetizing inductance, which will denote the energy required to establish the flux. Okay, so this will be lost as active power, whereas Lm will be an reactive component, so which will be required to establish the flux lines in the transformer. Because of this presence of inductance, the transformer always operates at lagging power factor. If we give an source which supplies current at UPF, on the load side, if you see, there will be a small lagging power factor because of this factor, because we have an Lm magnetizing inductor. Okay. So, in our discussion of non isolated DC-DC converters, there we will be considering this simplified transformer model. Okay. So, where we are only considering the Lm, although it will have all these components, but for our simplicity of analysis, we are only considering the magnetizing inductance. Okay. So, now the flyback converter, this is the basic isolated DC-DC converter. When the switch is closed, in this case the dot terminal will become positive. Why? The switch is closed. So, this is connected to this point. So, we will get plus at the instantaneous polarity of this winding 1. So, similarly on the secondary side, we will also have the positive over here and the negative will be over here. So, the diode gets reverse bias, or it will offer infinite resistance. Okay. So, while starting our analysis of this circuit, we have seen that we will be assuming steady state operation, and we are assuming the capacitor size to be very large, so that the ripple at the output stage can be neglected. We are considering the components to be ideal, and we are also neglecting the turn on and turn off time of the device. We are assuming it to be ideal. Then this is the equivalent circuit when my switch is closed, because this was positive. So, this is negative. So, diode is reverse bias. So, it will offer infinite resistance, or it is open circuited. Now, the current will be flowing in this path. Now, as there is no current in this path, so the reflected current will be 0 irrespective of my turns ratio. So, where this current will be going? Now, this current will be used to establish the flux lines in the core. Okay. So, it is nothing but Lm is storing our energy. Now, voltage V1, what will be the voltage across the winding 1? It will be equal to source voltage, because they are connected in parallel. V1 will be equal to Lm dILm by dt, because if you see they are in parallel. So, again it will be applied across the leakage inductance. Now, it will be as voltage is applied, so it will experience LdI by dt, or there will be an storage of energy, or the current will be increasing. With the same assumption of linearization, we will be considering small change in current by small time. So, this will be the change in your delta ILM value with respect to the switch on time period. Okay. Now, here ID is 0 because it is reverse bias. So, diode will not carry any amount of current. When the switch is open, now inductor was carrying current in this direction, in the downward direction. In the previous case, we know the behavior of this inductor. It will try to maintain the current in the same path. So, it will flow through this. Why? Because we have removed the gate pulse. Now, switch will offer infinite resistance. So, it tries to flow through this path. So, if I see, it is leaving the dot on the primary side. So, what is the conclusion? Now, it should enter the dot from the secondary side. So, it will try to enter. Can the diode carry current in this direction? Yes. So, now the diode will get forward bias, and now Lm will behave as a source, and it will transfer power to our load. So, this will be the equivalent circuit when the switch is open. So, your current will be flowing in this way and on this, in this direction, in the secondary side. Okay. Now, V1 will be equal to V2 N1 by N2, assuming the turns ratio are N1 and N2 respectively. So, now the V1 is nothing but the reflected secondary side voltage. Okay. So, what is V1 now? As the secondary side voltage will be equal to V0, that will be reflected on this one. And why it is minus V0? Because if you see, the dot was over here, but the plus side of the capacitor will be over here. So, we have an negative polarity at the output stage. Okay. Now, Lm will be equal to dIL by dt, because now if this inductor wants to force the current through this path, it has to overcome this opposition or the voltage which is there on the primary winding, that is the reflected secondary side voltage, has to overcome by this Lm, then only it will be able to feed the current, or it will able to maintain the current in this path. So, now with the same linearization approach, now we will be changing it to delta ILM by 1 minus d into t, this is the turn off time. So, if I simplify it, I will get the delta IL open value, as we are normally doing to find out the transfer function or the relation between input and output voltage. We will equalize the current, and it should be equal and opposite, or the sum of them should be equal to 0 for steady state operation. So, this Vs dt by Lm which we have found out both the equations equated to 0, we will find out that the relation between your input and output voltage is equal to V0 is equal to Vs d by 1 minus d into N2 by N1. Okay. So, if you remember this part, the part which is other than the transformer turns ratio, it is equal to the transfer function of an boost converter. Okay. So, here we have an additional turns ratio term. So, this is because of this presence of this additional flexibility with us, it addresses the limitation of limited voltage gain. Okay. So, now by adjusting the N1 and N2 value appropriately as per my requirement, I can achieve any amount of gain as per my requirement of the application. Okay. So, now going into the design of your diode. Okay. So, what will be the diode voltage rating and current rating? So, every device will have two components that will be required, that is its voltage and current rating. Okay. So, first let us see the voltage rating. So, in this case when the diode is in off condition, so it will be has to block one particular voltage. Okay. So, what will be that voltage which it has to block? It will be equal to the V2 plus your output stage voltage. Okay. So, because this two, when I apply KVL in this loop, I will observe that it has to block the reflected primary side voltage plus the capacitor voltage or the output stage voltage. Okay. So, if I assume the input and output voltage to be same, so the rating of this diode will be 2 times of my supply voltage, minimum rating. Okay. So, it should be more than that. Then when the switch is in the open circuit, so what will be the voltage applied across this? Again we have to apply KVL in this loop. In this case also I will find out that Vs and this reflected output stage voltage or the secondary side voltage, reflected secondary voltage, has to be blocked by the device. Again if I assume the source voltage and the output voltage to be same for simplicity, then it is again it has to block 2 times of our supply voltage. Okay. So, both diode as well as your switch has to be rated to at least twice of your supply voltage. Now, the current through it. Okay. So, what will be the current through the diode? The diode comes into picture whenever the switch is open. When the switch was closed, it was reverse bias and it was not carrying any current. Okay. So, in this case, what will be the diode current? It will be equal to minus of I2. Okay. Why? Because we have assumed I2 direction to be in this way. So, your diode is carrying current in this way. So, it will be equal to minus of I2. What is I2 now? It is I1 N1 by N2. Okay. So, this is my I1. So, that will be equal to the turns ratio or approximate transfer of your current from the primary side to the secondary side. We have to multiply with the turns ratio. Then we will get ID is equal to ILF by N1 by N2. Why? In this case, if you see, the same current is circulating in this path. Now, the minimum inductance value. Okay, or what should be my minimum value of Lm such that I can maintain the operation in the continuous conduction mode. Okay. So, for that again we will follow the same approach. We will find out the minimum value, then we will equate it to 0 to find out the critical value of the inductance, which will be just sufficient to maintain our continuous conduction mode of operation. Okay. So, here I minimum is nothing but average inductor current by delta IL by 2. Now, how to find out this IL value? So, we will go back to our power equation, that is input power will be equal to output power, because we have neglected the losses in the circuit. So, V0 square by R, that is my output power, that will be equal to Vs Is. So, V0 square by R equal to Vs IL into D. So, where IL will be given by this value, where we have replaced the V0 by the appropriate value which we have derived in the last slide. Okay. So, now I minimum will be equal to this IL average value minus of delta IL by 2, which we have also derived. So, when I equate it to 0, I will find that L minimum will be equal to this much. Okay. So, if I minimum is equated to 0 and solved, so we will find out that L minimum required or minimum inductor required to maintain continuous conduction mode of operation will be given by this relation. If in an application I see that Lm, the value of Lm which is used is less than this value, so you will go into DCM mode of operation or discontinuous conduction mode. If it is greater than that, we will be in the continuous conduction mode of operation. Okay. Now, capacitor design. If you see the output side of this circuit or output stage of this circuit and compare with our basic non-isolated DC-DC converter, we will see that it is having a similar stage like our buck boost converter. Okay. So, buck boost converter and this capacitor will be experiencing same type of operating condition. So, we can just use the same approach and see that the capacitor can be designed by using the same formula, that is V0 dt by R into delta V naught. Okay. So, where delta V naught is my performance requirement, as per the required ripple percentage, I will design the capacitor size. Now, what is the limitation of this one? Advantage wise, when we go into other isolated DC-DC converter, we will see that this flyback converter has the minimum number of devices. It is the simplest isolated DC-DC converter, whereas it comes with some limitations, that is the power. If you see how we have calculated the relation between input and output voltage over here, we have equated the charging and discharging current of our LM, or we have added them and equated to 0. So, if you see, in one half it is storing the energy, in the other half it is releasing the energy to the load. So, now LM is used as an buffer energy storing element. Okay. So, from our previous discussion, from where we have got this LM was inherently present inside the transformer. It was your magnetizing inductance. Okay. So, if I want to increase the power rating of this converter, I have to increase the value of LM, and for high power it becomes infeasible, or the flyback converter is not recommended for using in the high power applications. So, its power rating will be very much limited. So, where it will be used in our electric vehicle for auxiliary power supplies, or the add-on power supplies, or the add-on requirements, for those will be low power circuits. So, there we will be using this flyback converter, or the next one which you will be seeing, that is your forward converter. Okay. So, its application is limited to the auxiliary power supply of electric vehicle. Now, this voltage V1, so when the switch was on, it was experiencing the supply voltage. When the switch was off, it was experiencing the reflected output stage voltage. Okay. ILM, we have already seen this one. Source current, whenever the switch is closed, the LM draws some current to get charged. So, when the switch is closed, your source current will be equal to the LM current. Okay. Now, diode current, what will be your diode current? When the switch is on, diode was off. When the switch is off, your source is disconnected and diode sees the current. So, it will be equal to the LM current during the turn off time, which is from dt to t. Then your capacitor current. When the switch is closed, our diode is reverse biased. So, entire output current will be drawn from the capacitor from 0 to dt time. Then from dt to t time, your capacitor current will be equal to, it can be found out by applying KCL at this node. Okay. So, we are having an inward current through this, and outward current is fixed, that is I0 is considered to be ripple free, because we have assumed the capacitor has to be sufficiently large. So, it will be V0 by R. On this side, we know we have calculated the value of your diode current. Okay. So, just by applying KCL, the remaining current will be flowing through this capacitor. Now, as flyback converter, we have seen that it, although it was the simplest isolated DC-DC converter, but its power rating was limited, or it cannot handle high power. So, what if I want to use isolated converter as my major or the main converter in the circuit? So, the other way around is, the next solution is forward converter. Okay. So, in this forward converter, if you see, we have used 3 winding transformer instead of an 2 winding transformer, we have 3 winding transformer. The realization of forward converters are of different types. So, this is one way of realizing your forward converter, where we have used an 3 winding transformer. We can have other arrangement where the 2 winding transformer can be used, but we will have some additional switches or diodes to reset the LM. Okay. So, why we require to reset the LM? Because the first time when we discussed about your transformer in DC circuit, we have said that we have to reset our LM value. Okay. Or the transformer core should not be saturated. We should make sure that LM current is limited within the boundary, so that it does not go into saturation. Okay. LM is nothing but it is the representation of our core. Okay. So, if LM is saturated, it means the core of the transformer is saturated. So, here device wise, if you see, we have only one switch over here, similar to our flyback converter, but the number of diodes, if you see, we have 3 number of diodes. Now, we have an additional inductor at the output stage. Okay. Now, see the dots. So, dots are given on this figure. Okay. So, but what will happen when the switch is closed? Now, the moment I close this switch, my positive of the supply will be connected to the dot. So, my dots has become positive. So, all other dots will be positive at that point of time. What will be my states of diodes? First, we will start with our D1. Okay. So, if you see this positive is connected to the positive side of the diode D1. So, it will be forward bias, it is ready for conduction. If this starts conduction, what will happen to our D2? If we see D2, negative is connected to the positive side. So, it is reverse bias, and vice versa. Just now we have decided that D1 should be in the conduction mode. If D1 conducts, so this point will be connected to the positive side and this is connected to the negative side. So, obviously the D2 is reverse bias. Okay. So, what will happen over here? If you see the tertiary winding or the third winding, positive is on this side. So, positive terminal is connected to the negative side of the diode. So, D3 is clearly reverse bias. So, a positive voltage will forward bias D1 and reverse bias D2 and D3. Both of them will not conduct, only our D1 is forward bias. So, this will be the equivalent circuit. We have neglected this part because this diode is reverse bias. So, it offers infinite resistance. Over here we had the other diode which is again reverse bias. So, it will offer infinite resistance. So, there will be no current through these two components. So, we have removed them. So, now if we see the LM is experiencing an positive voltage. So, the current will start increasing in this way, and on the other side what will be the other component of current. Now, we have a closed path between the primary and secondary side. If you see this path is also complete, and on the source side also it is complete. So, whichever current is drawn on the secondary side, the reflected current will be drawn from the source. So, this will be the parts of current. Now, what will be the voltages? V1 will be equal to Vs. Clearly the switch is closed. So, V1 is directly connected in parallel with the source. So, it will potential will be equal to Vs. V2 will be equal to the turns ratio times of V1 or the reflected primary side voltage, which is equal to Vs into N2 by N1, because V1 is equal to Vs. Now, VLX, what will be the voltage across this inductor? So, if you see this, on this side we have V2, on the other side we have V0. So, it will be the difference between V2 and V0. What is V2? Just now we have found out, it is the reflected source voltage. So, it is Vs N2 by N1 minus V0. Now, in the same way, linearizing it, assuming higher switching frequency, delta ILX by delta dt, delta t can be replaced as dt because it is true when the switch is closed. So, delta ILX will be given by this. Now, analysis when the switch is open. Okay. So, what has happened in this previous case? If we see, this inductor was carrying current in this direction. So, the moment I disconnect the switch, it will try to maintain the current in the same way because of the property of inductor. So, it is circulating the current in this direction. So, now let us see the dots. So, if I see the current is leaving the dot, so it will try to enter the dot. Okay. So, if it tries to enter the dot on this side, so the diode, if you remember, the diode was connected in this way. So, now the current is flowing in the opposite direction. So, obviously, diode D1 will not be able to carry the current. Now, on this side, on the tertiary winding, can it enter the dot? Yes, if you remember, the diode was in this way. So, it can carry a current in this way. So, our LM current will be flowing through the tertiary winding. Okay. Now, why this diode is closed? So, if you see, we have an inductor over here also. So, it will also try to maintain the current. In the previous case, the current was flowing in this way. So, it will maintain the same current. So, what happens when the switch is open? Which devices will be reverse bias? Diode D1 will be reverse bias. Other two diodes, that is D2 and D3, will be forward bias, and the switch, as it is disconnected, it will offer infinite resistance. So, the current is flowing out of the dot of N1. So, it will be, we have seen the analysis, because of that D1 will not be able to carry the current, it will be in the reverse bias mode, and the other two diodes will be carrying the current. So, what will be the voltage across V3? So, in this loop, if we see the tertiary winding case, so here we will observe that the source voltage is connected in parallel with your tertiary winding. Okay. So, now in this loop, if I apply KVL, so let us see the path, it is through this loop. Okay. So, this is one loop which is completed. If I see, the source is directly connected to your winding number 3, but the polarity is reverse. Why? If you see, the dot is connected to the negative side of my winding. So, that is why we have minus Vs over here. Okay. So, in this tertiary loop, if I apply KVL, I will observe that the tertiary winding voltage will be equal to minus Vs. Now, V1, what will be the V1? The moment we have some voltage across one of the winding, the transformer action will hold true, the voltage will be reflected in the other two windings. Okay. So, what will be V1? It will be equal to the corresponding turns ratio into V3. Now we have found out the value of V3, which is equal to minus Vs. So this will be my V1 voltage. V2 voltage, similarly the reflected tertiary winding voltage with respect to the secondary side. Okay, the secondary side will see the tertiary voltage which is multiplied with its the appropriate turns ratio, which will again be equal to minus Vs into N2 by N3. Now VLX, what is VLX over here? If I apply the cable in this loop, this is 0 because the diode is in the on state and we have assumed it to be ideal. So in this loop, if I apply KVL, I will find out that the VL is experiencing negative of the output voltage. So if I apply linearization and I change the di by dt into delta ILX by delta t, where delta t is 1 minus d into t. So it will be equal to minus V naught by Lx. So now delta Lx open will be equal to minus of 1 minus d into t V naught by Lx. This is my delta Lx value when my switch is open. This was for the closed case. So in steady state, we know that the change in inductor current should be 0 or delta Lx open plus delta Lx closed should be equal to 0. So we will see the relation between our input and output as V naught is equal to Vsd into N2 by N1. Okay. So capacitor design for this circuit, again the output stage is similar to our buck boost converter. So the same formula can be used over here. So my capacitor can be designed from this value. Then the currents, okay. So when what will be the I1 current, okay. When the switch was closed, it was seeing which current? The reflected output stage current plus the LM current, okay. So what will be the current carried by I1? It will be equal to LM plus your I1 current, okay. So why LM will also be added to I1? Because it is flowing into the transformer, okay. So we have this source, so which will be feeding both the currents, so it has to come from the supply, okay. When the switch is off, what is happening? The LM current just circulate through this, so that is what will be carried by your I1, okay. So if you see, this is your reflected LM current or the current through your leakage magnetizing inductor, okay. So I2, what will be your I2? The secondary side carries current only when the switch is in the closed state. When it is open, your this diode was getting reverse bias, so there was no I2. So from 0 to dt time, it will carry the current equal to your I1 current with the respective turns ratio, okay. So the current will also be reflected because we have transformer in between, okay. The shape should be same, but the magnitude should be depending on the turns ratio. Now I3, that is the tertiary winding current. So when the switch was closed, it was not carrying any current, so it was 0 because the diode was off. But when the diode it gets forward bias, that is when the switch is open from dt to t naught, it will be able to carry the current because it will be flowing in this way, which the diode D3 can carry. So the tertiary winding or the third winding will be seeing current from dt to t naught. Here what is t naught? So if you see this t naught, so it is just closing before t time, okay, or our switching cycle is from 0 to t. T naught is the value at which my LM inductor is completely discharged, okay. What is LM? LM is the leakage inductance of my transformer, okay. So if the current through LM is 0, what is the meaning of that? The transformer flux is 0 or transformer core is completely reset, okay. So here if you see the fundamental difference between your flyback and forward converter, the current which was flowing through LM, in the flyback case it was responsible for power transfer, whereas in this case if you see, when the switch is closed, the reflected reflected load current is carried from or drawn from the primary side, okay. When the switch is off, the energy which was stored in LM is fed back to the supply, or the energy is recovered from the transformer and given back to the supply when the switch is off, okay. So now here LM is no longer an buffer energy storing element, it is just an unwanted component for us which is present with us because we do not have any ideal transformer. Because of the practicalities, we will get this LM value. Now it is no longer responsible for the power transfer. The major drawback of your flyback converter was because LM was used in the power transfer path, so that was putting a strong limit on our power handling capability of the flyback converter, okay. So forward converter will not have that limitation because now LM is no longer responsible for your power transfer. Now this T naught, can this T naught be greater than T or the switching time period. Is it necessary to make the flux lines perfectly 0 before the start of next cycle? Can I maintain continuous current through ILM, or can ILM be continuous? The answer is no. Why? In the flyback converter, it was responsible for power transfer. So, even if there was continuous current, that was used for your power handling. Okay, so it was doing some useful task. Okay, so over here, if you see, if the switch is on and the inductor is carrying some current, and before the start of next cycle, suppose it is not getting reset. So, in the first case, when we start the converter, suppose we had 0 flux lines. When the switch was closed, it created 10 flux lines, suppose for example. Then when the switch was open, my inductor was having sufficient energy, that is LM was having sufficient energy, it did not get reset while feeding the tertiary winding, and 2 flux lines were left with us. Okay. Now in the second stage, our dt time is fixed. So in the second cycle, what will happen? This will increase to 12, and after the second cycle, it will get reset to n value of 4. It will not go to 0. So what is happening? Slowly we are increasing the residual flux, and after a few cycles of operation, I will see that LM will get saturated or my transformer core will be saturated. Because of this saturation, or to avoid the saturation condition, we should make sure that the transformer core gets reset before the cycle start of our next cycle. Okay, so that will bring the major limitation for our forward converter. So we'll also see how to calculate the value of T naught in the next class, and we'll see how or what is the relation between the input and output voltage, and what are the limitations of this forward converter in details, and we'll see what next we can offer as our upcoming solutions. Okay. Now in this class, what we have seen the flyback converter and the forward converter, which belongs to the family of isolated DC converter. We will always have an high frequency transformer. Why you use high frequency transformer? Because the size will be less. Flyback converter was characterized by low power handling capacity, because LM was used as a buffer element. We have seen the next solution where LM is no longer used as the buffer element, that is our forward converter. We have seen various waveforms and its basic operations. We will continue from this point in the next class. Thank you.